by golly, I'm going to try to make sure we do. And here we go. Cut that down before we go deaf.
Okay, today we're going to talk about the mole. Now I know what you're thinking. I know what a mole is. It's a small, furry creature that digs holes in the ground and destroys gardens. And some of you might be thinking that it's a growth on your aunt's face with hair sticking out of it. Well, in this case, a mole is a concept that we use in chemistry to count molecules, atoms, and just about anything extremely small. Have you ever wondered how many atoms there are in the universe?
What was that constant? 6.02 times 10 to the 23rd.
Atoms, just about anything extremely small. Have you ever wondered how many atoms there are in the universe, or in your body, or even in a grain of sand? Scientists have wanted to answer that question, but how do you count something as small as an atom? Well, in 1811, someone had an idea that if you had equal volumes of gases at the same temperature and pressure, they would contain an equal number of particles. His name was Lorenzo Romano Amadeo Carlo Avogadro. Wonder how long it took him to sign autographs. Unfortunately for Avogadro, most scientists didn't accept the idea of the atom, and there was no way to prove he was right. There was no clear difference between atoms and molecules. Most scientists looked at Avogadro's work as purely hypothetical and didn't give it much thought. But it turned out he was right. By late 1860, Avogadro was proven correct, and his work helped lay the foundation for the atomic theory. Fortunately, Avogadro died in 1856. Now the thing is that the amount of particles in even small samples is tremendous. For example, if you have a balloon of any gas at 0 degrees Celsius and at a pressure of 1 atmosphere, then you have precisely 602 sectillion gas particles. That is, you have 6 with 23 zeros after it, particles of gas in a container. Or in scientific notation, 6.02 times 10 to the 23rd particles. This example is a little misleading because gases take up a lot of space due to the high kinetic energy of the gas particles, and it leaves you thinking atoms are bigger than they really are. Instead, think of water molecules. If you pour 18.01 grams of water into a glass, which is 18.01 milliliters, which is like 3.5 teaspoons of water, you'll have 602 sectillion molecules of water. Since Lorenzo Romano, never mind, Avogadro was the first one to come up with this idea, scientists named the number 6.02 times 10 to the 23rd after him. It is simply known as Avogadro's number. Now, back to the mole. Not that mole. This mole. Yep, this number has a second name, the mole. Chemists use the term mole to refer to the quantities that are at the magnitude of 602 sectillion. This is known as a molar quantity. Atoms and molecules are so small that chemists have bundled them into groups called moles. Moles are hard for students to understand because they have a hard time picturing the size of a mole, or 602 sectillion. It's just too big to wrap our brains around. Remember our 18.01 milliliters of water? Well, that's a mole of water. But how much is that? Exactly what does 602 sectillion look like? Maybe this will help. Exchange the water particles for donuts. If you had a mole of donuts, they would cover the entire Earth to a depth of 8 kilometers, which is about 5 miles. You really need a lot of coffee for that. If you had a mole of basketballs, you could create a new planet the size of the Earth. If you received a mole of pennies on the day you were born and spent $1 million a second until the day you died at the age of 100, you would still have more than 99.99% of your money in the bank. Okay, now we sort of have an idea how large the mole is. So how do we use it? You might be surprised to know that chemists use it the same way you use pounds to buy grapes, deli meat, or eggs. When you go to the grocery store, you don't go to the deli counter and ask for 43 slices of salami. You buy your salami by the pound. When you buy your eggs, you buy a dozen eggs. When we hear the word dozen, we probably think of the number 12. We also know that a pear is 2, a baker's dozen is 13, a gross is 144, and a ream of paper is, anybody? A ream is 500. Well,
All right, so he's basically showing you how this word rings a bell of a number. So a dozen, we all know just means what? 12. And so we're starting to learn that a mole, when I say mole, it means huge number, 6.82 times 10 to the 23rd. It's an association between a word and a number. And so you'll hear that a lot. We're going to talk about molar conversions in a bit too. So
a mole is really the same thing. For a chemist, a mole conjures up the number 6.02 times 10 to the 23rd, not a fuzzy little animal. The only difference is that the other quantities are more familiar to us. So there you have it, the story of the mole, Avogadro, basketballs, and how to buy salami at the grocery store.
All right, so let's talk about some of the things you maybe wrote down. Lauren, give me something you wrote down.
I said there was no clear difference between atoms and molecules.
Okay, so at the time when Avogadro was working, they didn't know there was a difference between these particle types, but now we do. We know that atoms make up molecules. So there are actually 3 particle types. Write this down for yourself. 3 representative particles that we will use when we say a number of things. Instead of just saying particles, or instead of just saying things, we're actually going to put a name to it, okay? So there are 3 things we call representative particles. You just told me 2 of them. Atoms and molecules. Okay, so atoms is a term that's used to describe some part of matter. So give me an example. An atom of what? Give me something from the periodic table. Potassium. An atom of potassium. So we're just going to say an atom of an element. So it's something straight off the periodic table. But if I use the word molecule, we learned this last week, what were we actually referring to? What kind of compounds? Covalent compounds. Good. So molecules are used to describe covalent compounds that come together with nonmetal nonmetals. What was the other particle type that was used to describe ionic compounds? Formula units, right? So remember we wrote FU? Did you guys write that down? Okay, cool. So you have your 3 types. Atoms describe simply elements. Molecules describe covalently bound molecule or compounds, and formula units describe ionically bound compounds. Okay, so back then they didn't know there was a difference, but now we actually know there's a difference. So we still call them particles, but they come in 3 flavors, and so it gives us some elaboration there. Isabella, what did you write down?
I had thought that if you had an equal amount of gas, the volume that the particle numbers are equal.
Okay, so and I kind of wrote down that here as well. So on the bottom of the board, he said if you had equal volumes of gas, which they said it, but they didn't write it down, 22.4 liters of gas at 0 degrees Celsius and one atmosphere, so they give us a pressure and a temperature. They said they have equal amounts of particles. Well, those particles were actually the same number of particles as in a mole of particles, which is 6.02 times 10 to the 23rd. So I'm trying to do some basic outline of information for you, and then we'll kind of jump into the details. So it's kind of our reading guide we're doing partially together. So one thing he mentioned was the word molar volume, which is what the example was with the equal volumes. Write down that molar volume. 1 mole of a gas at 0 degrees Celsius and 1 atmosphere equals what volume? I just told it to you. 22.4 liters. All right, so we're getting back into the math side of things, but we're starting to kind of get a grasp of how we communicate this information using our chemistry nomenclature. So we'll start to name our gases and name our ionic compounds as we go. So 1 mole of gas at these specific conditions is equal to 22.4 liters. But what's in that mole of gas again? 6.02 times 10 to the 23rd molecules, because in this case we're talking about a gas, and many times our gases are covalent compounds. So we're starting to make some equivalencies, right? So 22.4 liters of a gas contains 1 mole of that gas, which is actually 6.022 times 10 to the 23rd molecules of that same gas. So these things are all equivalent to each other. Starting to go back to a little dimensional analysis. Like I could say 1 foot, and you say, what's equal to 1 foot? 12 inches, which is how many centimeters? 26 or something like that, 26, 27 centimeters, which is a third of a yard, right? All these things are equivalent, yeah.
I was just wondering if you're talking about formula units, it would still be like 6.02 times 10 to the 23rd formula.
Yeah, if you were talking about ionic compounds, certainly. All right, tell me, Cassandra, tell me something you wrote down.
I said that if 602 sextillion is like molar quantity.
Okay, so it's the molar quantity, meaning a number of things, right? So that kind of goes back to this question 1. What are 3 ways to measure matter? What are some ways that we can get a quantity associated with, let's say I go to the store, I'm like, all right, guys, I need you guys to get me some bananas. They're like, how many? You know, a mole of them. What would you be doing? Say again? If I say give me a mole of bananas at the grocery store.
You'd be
So how would you do that? You would literally count 1, 2, 3. You buy all the bananas in the entire world plus like other planets, right? So you could literally count and get a number of items, which is going to be related to Avogadro's number, counting a molar quantity out. But I ain't got time for that, right? So what do you normally do at the grocery store if you're trying to get some maybe fruit or vegetables? Maybe weigh them, right? So what if I said a mole of bananas weighed, say a mole of bananas weighs, I don't know, 13 grams. That's way small, but work with me here, okay? So 13 grams. Instead of going, let me count all these out, you just probably go weigh it, right? So you could also mass whatever the quantity was that you're looking for, that's equal to the mole of bananas I told you, because I told you the conversion. I told you 1 mole of bananas weigh 13 grams. But what about apples? Apples are smaller, right? So what would a mole of apples probably weigh? 10 grams. What would a mole of raisins weigh? 5 grams. So you see all these different quantities, masses are going to be associated with different things. So I can give you potassium and carbon and nitrogen. I say, okay, what's a mole of that weigh? The mole of what it weighs actually is already on the periodic table. What does 1 mole of carbon weigh? 12.01. Normally we used to say AMUs, right? Atomic mass units. Now we're actually going to switch the name of it. We're going to call it grams, just as a mass term. What does chromium weigh? What's 1 mole of chromium weigh? Look at the periodic table, people. 51.99. What's 1 mole of water weigh? Water.
18.
How are you getting that?
2 hydrogens and 1 oxygen.
2 hydrogens, 1 oxygen. Weigh out your hydrogen plus 1, plus another 1 from your hydrogen plus, how much does oxygen weigh? 16. So 1 plus 1 plus 16 is 18. That's something called molar mass. And you've heard molar mass before, and we've actually done it before. Now we're actually going to use it for real. Okay? So I can mass things out, and they're all going to be equivalent based on what I've told you we're considering. And the last thing is to get the volume. So if you were really cool, you take your huge graduated cylinder to the grocery store, and I said, I'm like, okay, guys, I want 3 liters of bananas. And they're like, what? I bring the huge graduated cylinder, do some water displacement, pop the bananas in there. Okay, I got 3 liters, done. Now that's not obviously what you actually do, but you could also get the volume of something, and likely it would be in liters. And you just heard me say liters down here. What was the number that went with liter? 22.4. So there are 3 key numbers in this entire ordeal. We're getting to them. Okay, last thing I want to talk about is, what does STP mean? It means standard temperature and standard pressure. Have we talked about a temperature and pressure yet? Yeah, what did we write down? Okay, so that gas at STP, or the gas at 0 degrees Celsius. What's that in Kelvin? Go higher. Yeah, so when you take Celsius to Kelvin, what do you do? What's the main difference? Add 273. So 0 degrees Celsius is 273 Kelvin. Okay? What was the pressure I just talked about? Say again? Right, it's 1 atmosphere, right? So standard pressure is equal to 1 atmosphere. 1 ATM is how we abbreviate that. All right, so that's the background of stuff that you would have gotten from your reading. And there's a little bit more there, so I definitely think that you should go back and check out some of those as we go. But we're going to actually walk through some examples today, okay? So write down, can I go forward? Okay, so I basically did part of the reading guide for you guys. Write down this. This is called my mole map, okay? Write mole, make a big little bubble map. And of course, you have the back of your paper, but you're not going to have enough room for all your notes, so you might want to mix your paper out. Okay, so one mole can be related to, just like we were doing with the grocery store example. If I said I wanted a mole of bananas, what was the first thing you guys said that you would do? Count them out, right? Well, a mole of bananas could be equivalent to a mole of particles. So the 3 types of particles are formula units, atoms, and molecules. So I would definitely recommend you label this whole thing up here representative and they come in 3 flavors: atoms, formula units, and molecules. So how would I get the number of particles I was looking for? One more time. What did you say you're going to have to do? Count them out to what? So give me that in scientific notation. Times 10 to the 23rd. The relationship between 1 mole of anything and the number of particles you would actually count out is 6.02 times 10 to the 23rd things. So there's a relationship there with a number. That's the constant that relates them. Okay, let's go down to the bottom part, and I'll come up to the other one in a second. I'm bored. Okay, so at the bottom it says STP, molar volume. So 1 mole is related to a volume of a gas at STP. What's STP one more time? Standard temperature pressure, which is how many Kelvin? 273. And what pressure? 1 atmosphere. Right, you gotta say the unit with it. 1 what? 1 cookie? Like, it's not pressure, right? So what's the relationship between 1 mole of a gas and the molar volume it takes up? There's one number we said with volume. 22.4. 22.4 liters is equal to 22.4 liters of a gas is equal to 1 mole of that same gas. And how many little particles are in that 1 mole of the gas?
2 times 10 to 24.
Right, so you can actually relate that back to the particles, which is the top of this little bubble map here, okay? So those are the 2 main numbers you will see constantly. Those 2 right there. Now, molar mass, you actually have to get from the periodic table, and it actually is a mass. So if we're talking mass, generally what unit would be used with that? Grams. So I could say some number of grams of this particular compound that we're talking about is equal to 1 mole of that compound. And that's what Bradley just did for me. I said, give me the molar mass, or the mass of water, H2O, and you guys went to the periodic table, hunted for H, hunted for O, 2 of the H's, 1 of the O's was 1 plus 1 plus 16, which was 18 total. So let's do the same thing. What's the molar mass of lithium chloride? Lithium chloride. Give me an approximate. How are you getting 42? So 6.9 something from lithium plus 35.45 from chlorine, about 42. But you'll notice it's different for every compound. I can give you different. I could say lithium chlorate, and what would you have instead? What's the formula of lithium chlorate? Give me the whole shebang. So what's lithium weigh? Yeah. 6.94. Okay. What's chlorine weigh? 0.45. What's 3 oxygens total weigh? 3 times what? 16. You guys have calculators in the middle of your table. Get it out. Tell me the mass, total mass, molar mass of lithium chlorate. 72 plus 48 is 48 plus what?
42.
Oh, I thought we were sorry. I thought you were thinking. I was thinking 72. Yeah, that sounds right. 90ish. Yeah. So that's total about 90, and of course we would have sig figs. We'd have like all of our numbers out. About 90 grams per mole is what we would title that. Grams per mole is how we denote molar mass. So the number of grams, it has to be pulled from the periodic table. So I'm not putting a true number there because it's not a single number like the other ones are. And we'll always establish it as grams per mole when we write it out. Okay, you with me so far, guys? Count things, mass things, look at the volume of things. That's it. And they're all related back to 1 mole. Okay, so this is your friend for a while. Now that first number you wrote down, what was the first number on the top of the chart? Beautiful. That's called Avogadro's number, or Avogadro's constant. Go figure, the guy's name was Avogadro. Like, who thought we would have had a scientist name something after them, right? Okay, molar mass is our next conversion, which, what was the unit for molar mass? Grams per 1 mole, right? It's always per 1 mole of our compound we're talking about. The number of grams will vary based on what we actually are speaking of. And then what's the unit for volume of a gas? So just give me the unit. Liters, right? And then, of course, if we were converting it, we would say 1 mole of the gas weighed 22.4 liters. So those are the only numbers. Just make sure that you're thinking about if I'm talking about mass or volume, I'm using grams and liters. And then Avogadro's constant is representing a true number, which is why I don't have a unit here yet. But when we start to speak of specific things, we will put a unit there, be it atoms, molecules, or formula units. It's just going to be based on what we're talking about. Thumbs up when I'm good? Okay, so that's just no Avogadro's number is that number we've been saying. Okay, so this is on the front side of your notes. Okay, so this gives you a little context to like putting this number into perspective. The SI unit for the amount of a substance is what we're talking about now, the mole. So that is an SI unit, which is why we do speak of these things in the weird units that we kind of talked about. And so it allows us to convert between. The definition of mole allows us to convert between 1 mole and give me something else. What were one of the 3 conversions we just kind of showed off our bubble map? Mikado, tell me something.
Mole mass.
Okay, so 1 mole and mass. We can also convert between 1 mole and Syrian. Tell me something else. Give me one of the 3 branches. What did you just say?
I said volume.
Volume, sorry, I was talking as you were saying. Okay, so we can convert between mole and mass, mole and volume. What's the last one? Ansley.
Represented particles.
Right, I'm just going to say particles for short here. And number of particles. So 1 mole can be related to those 3 things in those 3 ways we just wrote down. All right, so again, the representative particles. I don't think I have this on your paper. This part. Okay, you've already written this down on your back of your sheet when we're kind of talking about the warm-up. There's only one thing I really want to add to this. So we just said atoms refer to elements from the periodic table. And then a molecule refers to covalent compounds, and formula units refer to ionic. The only thing we haven't talked about yet are what are the 7 diatomic molecules. You actually wrote these down on your reading guide 8. I may have talked about it one time. Do you guys remember these? It was a big 7, write this down on your paper, the big 7, and hydrogen. So hydrogen's here. Who's in the big 7? That's diatomic. Nitrogen's my beginning, and then oxygen, chlorine, bromine, and iodine. Guess how many there are? 7. 1, 2, 3, 4, 5, 6, 7. And so when I mean diatomic, I mean 2 atoms. So when I write them all by their lonesome, I actually do mean H2, N2, O2, F2, Cl2, Br2, I2. So, and since you guys have already drawn this, speaking of our bonding stuff from last week, you can think about this as a hydrogen bonded to a hydrogen, or a nitrogen that has a triple bond bonded to a nitrogen. So we know what they look like, we just have never written them out like this before. And so this actually means like 1 nitrogen atom bonded to another nitrogen atom. So what I can say is, within this compound, I have 1 molecule. Why am I saying molecule? Because it's covalent. 1 molecule of N2. How many atoms of nitrogen are in that? Say again? 2. This is an equivalency that I can see from a picture, actually. 1 molecule of nitrogen into diatomic nitrogen is equivalent or contains 2 atoms of just plain old elemental nitrogen in it. So we can start to make these our own equivalencies based on how things look because we've drawn our structure so much now. Okay, so keep that in the back of your mind. All right, so, and these are just some more images of what this looks like. So, what's Cr2O72 minus? That's just a plain old polyatomic atom. Anybody? That's dichromate. What's NH4? Whoa. This is our 1 rando polyatomic that's got a cation. Say again? Ammonium dichromate is what that is. Ammonium dichromate. Woo! All right, name this guy. Cr2O3. There's no charge there, right? There's no charge, so it's not just simply a polyatomic, it's actually a compound. I'll wait on you guys. Let's go, guys. Are you recognizing as ionic or covalent or an acid? Ionic. Chromium. Chromium's like chrome wheels, man. Think of metals, right? Shiny. Chromium 3 oxide. That was on your quiz. Okay. That's plain old nitrogen, and that's, I know you know this, dihydrogen monoxide, aka water. All right, so, but what I'm showing you is that you can actually think about these things in 3 ways now. A mole of that weighs 252 grams. How do you think I got that number? And added up all that crap together, right? And then equals 1 mole, which is 6.02 times 10 to the 23rd. Formula units. Why am I saying formula unit now? Because this is ionically bound. But then over here, I still have just a little N2 over here. I still have 6.022 times 10 to the 23rd. But I'm saying molecules because I'm talking about a covalently bound compound. But it weighs 28. Well, why does a mole of that weigh 252 and a mole of that weighs 28? Right, and just in general, I got 2 atoms here versus like, I don't know, a bunch of atoms over there, so 20-ish or so. So it weighs a lot less because I only have 2 atoms here, but their number of particles are still the same because I'm still talking about a mole of something. Okay, so I think you're getting there a little bit. Let's practice this a little bit more. All right, so let's do our molar mass discussion first. Do I have that here? I may have just skipped this. All right, so let's practice the molar mass of a couple things first. I actually want to do, what's the name of this? MgNO3 magnesium nitrate. Find magnesium. We're going to just do one example of a molar mass together. You guys have your calculators in front of you. What's magnesium weigh? 24.31 grams. Okay. How many nitrogens are there here? 2. This subscript, so this is a good point. Subscripts will distribute. I don't know what the parentheses are. They'll distribute to the inside of a parenthesis. So the 2 goes into the N. So there's 2 nitrogens, each weighing what? Well, each weighing what? 14. I'm going to write down all my baby steps here, okay? So 14.00 is what nitrogens weigh. This is a magnesium. How many oxygens do I have? 6. So you do distribute. So that's 2 times 3. So 6 times 16.00, which is our oxygen. So that's 3 oxygens. All right, so 24.31 plus 28 plus, what's the total? Can I get a second that? I'm not calculating with you guys. Should I be? Anybody confirm or deny? It's not that I don't believe you, Mikado. It's just, say again? 148 point what? 32. Okay. So that is 1 mole of magnesium nitrate. 148.32 grams of magnesium nitrate equals 1 mole of magnesium nitrate. This conversion has mass in it, so which conversion type do you think that is? Think of our 3-pronged approach. So what's the gram per mole one called? There's a name, a phrase we use for it. Molar mass. This is the molar mass. And now it should make sense. Mass per mole. Molar mass. And so it's kind of the phrasing kind of tells you what you're looking for as well. Let's do a harder one. Name that for me. NH4 2S. Ammonium sulfide. Okay, add up the mass. You need to distribute. You need to think about what has what subscript. This is the easiest thing, but you can easily get it wrong if you don't practice with me. I should see calculators in your hands. Or sharing with a friend. Put in all your decimals from the periodic table. So there's 2 nitrogens plus how many hydrogens? 8, because there's 2 distributes into the 1 next to nitrogen. This 2 distributes into the 4, so that's 8 hydrogens. And how many sulfurs? Just 1. Okay, so what's our total? 68.154 grams per 1 mole of ammonium sulfide. So you're starting to see where these things are now written as equivalencies. All right, so molar mass isn't too bad. You do need a periodic table. Please don't try to think about masses and mess up by trying to memorize those. You guys have periodic table. You have enough to memorize in your head. All right, so I'm going to skip that for a moment. We just talked about that. Okay, now we're actually working through a couple of problems. So some of these things I went through the notes first with you, so you had them in front of you. These are conversion type problems like we did back in Unit 1. So I told you the mental analysis would come back because there's a method to how we look at the math relationships between chemicals and what do we see in a lab versus what do we see like in the real world. So the math relationships all come back to basic dimensional analysis. So now that you know the 3 approaches, the first one is mole relates to particles. What's the second one? The mole relates to mass, and the mole relates to volume. This is really your only 3 approaches that you will take to do your stoichiometry, which we call it stoichiometry, but it's just chemistry math. So let's look at this couple examples together. We are going to think about what's our question, aka our unknown, and what's our given, and let's walk through the process first using our little map. Okay. So what's my question here? Looking for what? Moles. So write down for yourself, question mark. I want you to do this because I promise you it will help you. Because you'll get lost in a problem. This one's easy because these are simple ones, but we're going to get into more complex ones. So we're looking for mole. Okay? So we know mole is related to all 3 of those things, so that's going to be really easy. This is likely just going to be a single step problem. What are we starting with? What's our given? 2.80 times 10 to the 24th atoms of Si, silicon. Okay, look at your little mole map. Is there a direct relationship between atoms and mole? Yay or nay? Yes, and what is the connection that connects those? 6.022 times 10 to the 23rd. You've written this down about 5 times now. So I'm going to write the mole map up here. But we're basically looking at this relationship here between mole and particle. So on the top of our fraction, we want to get the unit we want. What unit do we want? Whoa. What unit? Mole. I want 1 mole of silicon. Just 1. All of these are related back to 1 mole. All right, so I want moles of silicon on top. I want to cancel out atoms, right? Because remember the top and the bottom cancel. So atoms is going to go down here. And how many atoms equals 1 mole of silicon? 6.02 times 10 to the 23rd. And you'll see me write 6.022 times 10 to the 23rd is how I learned it back like my sophomore year of high school. I can't get it out of my brain. That's just how I say it. So you'll see it written either way. It'll be fine in the end though, because our numbers will be close. Okay, so calculator up. Let's go. Calculate. So what you're writing here, or putting in your calculator, because atoms of silicon cancel with atoms of silicon, and we've achieved our moles. Yay, we got our moles there. What are you putting in the calculator? What did you say, parentheses? Oh, good. You guys remember, put your parentheses around your scientific notation. 2.80 times 10 to the 24th, parentheses, divided by, go stand up at the lab station. You're getting sleepy. Yeah, you. Divided by 6.022 times 10 to the 23rd, end parentheses. Anybody? 4.65 what? Moles of silicon. Yes, we're good here. So that should make sense because that's a huge number and that's a huge number, but that's just a little bit bigger of a huger number. So that makes sense. I had about 5 of those because that's 10 to the 24th, whereas this is 10 to the 23rd. You look at the ratio. That makes sense. Double check that it makes sense. So other than that, atoms and atoms cancel, mole is remaining, so we wrote down moles of silicon at the end. That's our conversion. And how did I know this relationship? Because this is a constant, but I also know there are only 3 of them, right? There are only 3 that we're working with right now. Okay, let's move on. Moles of potassium to grams. So what's my question? Question is grams of what? Potassium. So put K, grams of K. That, if you first recognize your question, it already sets you up for success because it shows you know what you're looking for. Okay, so what do I want to start with then? What's my given? 0.32 moles of potassium. Okay, we're looking at moles right now. We see grams as our final destination. Is there a relationship, a direct relationship between mole and gram? There is. What is it? Yeah, the mole equals whatever the mass is of that compound that we're looking for. So where would I find that information? Periodic table. Okay, so let's go ahead and set up our fraction first. What definitely do we want on the bottom? Why mole? Right, because I want the mole to cancel and I want grams on top. What do I always put with the mole? 1. Okay, 1 mole, because it's easy to keep that as a constant. 1 mole of potassium has how many grams in it? 39.10 grams potassium, and I pulled that from the periodic table. Okay, and so now what do I do? Am I done? Yeah, I'm just going to multiply. So my mole of potassium cancels with mole of potassium. I got grams of potassium, yes, right there. I'm good, I'm on top. And then what do I get when I calculate? What? Again? Oh, I thought somebody said 4.5 again. I was like, that's too similar. So 12 point what? 512. And so let's go back to sig figs for a moment. So the first one worked out, so we had 3, we had 3. How many sig figs are here? 2 sig figs. Okay, this one has more, but that's besides the fact. Round this to 2 sig figs. Say again? 13, yeah. So the 12 stays, right? But you just look over the hill and go, oh, there's a 5 there, so what happens here? Rounds up, so that's 13. And that has 2 sig figs in it. I know we were out of sig fig world for a little while and you missed it. We're back, guys. Okay. So, name SO3. Name it. Whoa. If it doesn't have an ion charge, it's not a polyatomic ion. It's just a normal old sulfur trioxide. This is a covalent compound. Covalent compound, right? So if it said that would be sulfite. But that's not how it's written. It's written as just a normal non-metal combination. Okay, so we'll keep naming as we go. All right, so I have a weird thing now. Atoms of oxygen I'm looking for. Do you see atoms of oxygen here? I see a molecule. So we're going to have to think out of the box on this one. So I have atoms of oxygen. So question mark atoms of just plain old O. Okay, I'm starting with what? Easy, okay, right here. Or as my 4th period says, easy money. Right here, SO3. Easy money. Okay, so we know how to start. We know we have to write down the given. But let's think ahead before we start writing. I know that I can get from moles to atoms. What's the mole? And so an atom is one of the 3 types of particles, right? If I were just going just from moles to atoms, what would be my one conversion? 6.022 times 10 to the 23rd, because that's how I get from moles to particles. But I actually have to break this down a little bit further, because I actually have a mole of a compound, not just the oxygen. So let's just go to molecules first. And why am I saying molecule? Because it's covalent. Okay, good. You guys are good at identifying. So if I just want to go to molecules, I know I'm going to put molecules on top. And do you write out molecules because you won't know if you're writing molecules or moles or you just put MOL. Okay? And then I know I got to get rid of mole. Mole's got to go on bottom. And put SO3 on both of those to label what we're talking about. Okay, so which of these gets a 1? Mole, because I'm always comparing everything to 1 mole. So 1 huge mole has how many molecules in it? 6.022 times 10 to the 23rd, right? Avogadro's number. I'm counting molecules out. Okay, so we've taken our just huge mass and we've said, okay, in that amount of stuff, I've got 1 mole, which is equivalent to 6.022 times 10 to the 23rd. And of course, I've got more than a mole. So let's say I got more than 6.022 times 10 to the 23rd molecules. But now let's hone in on 1 molecule. What does it look like? What's SO3 look like? Think of its Lewis dot structure. Good job, guys. S in the middle. Keep going. There's 3 oxygens, okay. And it probably has a octet and a double bond. I counted the valence electrons before, so we've drawn this before. There we go. Okay, we know how this looks. So I can look at it. In one sulfur trioxide, how many oxygen atoms are in it? 3. So let's write down exactly what we just said. In one molecule of sulfur trioxide, because now I'm looking at one molecule, just one little guy, how many atoms of oxygen were in it? 3 atoms, and I counted them, 1, 2, 3, of oxygen are in it. So this is where we got crafty. We were like, okay, I know how to get from mole to just straight up molecules. That's one conversion, that's 61022 times 10 to the 23rd. But then you're like, how do I get from a whole sulfur trioxide molecule to atoms of oxygen? You have to think about how they're related. One molecule has stuff in it. Well, that stuff is atoms. And so knowing what I mean when I say molecule, what I mean when I say formulate it, what I mean when I say atom, it's really helpful to visualize that, so this conversion you can pull out of your head and it's correct. Okay? So now let's calculate. Oh, sorry, let me cancel first. Moles, sulfur trioxide, gone. Molecules, sulfur trioxide, gone. Atoms of oxygen, yay. Okay, so that's our kind of like pat on the back, and then we go ahead and calculate. Any takers? It's helpful if you practice, because if not, your muscle memory is not there. I'll probably do one more example, guys. Thank you. 2.05 what? 9. Okay, times. Oh, I did 022. I'm not sure if you did. Times 10 to the 24th atoms of oxygen. Okay, so then how would I, or what kind of sig fig am I looking for here? How many? 3. This has 3 sig figs right here. This is a constant. Ignore it. It's huge. This is not truly a measurement. It's more of a counting and looking at molar relation or ratio relationships. So this needs to be to 3 sig figs. So what do I do instead? Yeah, 0.6. Okay. Let's do one more. And 2 more. I'm going to actually finish all these right now. Okay, write down your questions. Are there some extra calculators in bins someplace? Can you guys look? Zach can grab his calculator. Sophie, is there one in the middle? No? Okay. No more? All of mine are dead to doorknob. That's cool, never mind. Okay, so your question is what, guys? Grams of what is the heck is sodium phosphate? Na what? Okay, I hear PO4, because you know what phosphate is. Okay. What's the charge of phosphate? 3 minus, but where do I put it? Okay, guys, if that one has a charge, doesn't this one? Yeah, so if they both have charges, what do you have to do with the charges? Yeah, you have to crisscross. This is sodium charge of what? +1, it's in group 1. Phosphate charge of 3 negative. Crisscross, what's the formula? A3P41, but nobody writes the one because it looks dumb. Okay, move on. What do I start with? 4.52 times 10 to the -3rd. This is on your paper as well, guys. Mole sodium phosphate. Okay. Whew. Formula is half the battle, right? Because after that, we have our 3-prong approach. We have to particles, we have to mass, and we have to volume. So I have moles here. Hey, and I'm just going to grams. How many steps is that going to take me? Just 1, because is there a direct relationship between mole and mass? Yes, right there, molar mass. Does it have a specific number that goes along with it? No. How do I get my number? Find it on the periodic table. Add up sodium phosphate. Go. This is why I say get a calculator. What's phosphorus? 30.97. Yeah. All right, so I hear 163.94. Can I get a second? Can I get a third? Okay, cool. Where do I write that number? Why on top? Right, okay, so I'm hearing 163.94 what? Grams, right? And I'm going 2 grams. Grams has to go on top. So that's 163.94 grams of sodium phosphate. And that's equivalent to 1 mole of that sodium phosphate. I'm not sure if that was an L or a N, so make sure we're okay. So at that point, I've already see that the mole of sodium phosphate, the mole of sodium phosphate can cancel. And the grams lives on. Yay, that's what I wanted to get, so I know that I'm correct. Calculate. And then think about it as you go, and I'll refresh your memory and what I mean by that in a second. Answer? 0.741, is that what you said? 0.741 grams of the sodium phosphate. How many sig figs are here? 3. How many sig figs? Actually, no, this one's got more, so it's fine. Most time molar mass has like 3, 4, 5, 6. Kind of, they've got a lot of decimals, so we don't worry too much. Ooh, not for me. Some angry person knocking my door. All right, so 0.741. Does this make sense? Look up here. Does this make sense? Is that even a full mole?
No.
Not even close, right? So it's, of course, very small. Please begin the next one. Go.
Congratulations, Priscilla. You won that TV Titan Award for being rigorous and challenging.
Oh my gosh, thank you. I'm so keep going because my husband is angry knocking on my door.
Yeah.
Thanks, guys. Appreciate it. Congratulations. Thank you. Hey guys, rigorous and challenging. Who would have thought? While they finish up the last 2 examples, absolutely here, guys. Everybody stand up. Everybody stand up. Let's go. Oh. All right. In here. Hurry. I don't really want to. I'm sure you are. I was well, that was fun. Knocking on my door. I was like, where did he go? He just like disappeared.
They're like, can we come in? I was like, what?
You're like, I don't know. I'm not sure. Well, thanks, guys. I'll read you guys off some comments in a second. Sweet. Okay, so, yeah. Rigorous and challenging. That's me. Okay. So, you're starting off with what you're given. We got like 2 more examples I'd love to do with you guys. Liters of, ooh, what's that guy?
That's a molecule.
Formula. CO2. We've seen this one as a prefix. It's an easy peasy covalent one. We're looking for atoms of oxygen, so not the same thing, right? So remember how we drew the other one and kind of looked at the relationship? We're going to do the same thing. So we have a question, atoms of oxygen. All right. So I know I can get from liters to what's my stepping stone, basically for every single thing. Hold on. Liters. Liters is volume, right? Okay, so that's the one we haven't used yet, right here. Mole to volume. What's that relationship? 22. What do I write the 22.4? What's it go with? Liter, right? So top or bottom? Bottom, because liter has gone bottom. Okay. 22.4 goes with the liter, and that's related to what? 1 mole. So you're going back to that mole map you drew for yourself. There's only 3 relationships, and you can't go horizontal. You got to go back to mole, back to mole, back to mole. Okay, so 1 mole of CO2 and 22.4 liters of CO2. Those 2 things are equivalent, apparently, in SDP. All right, so liter cancels, liter of CO2 cancels. I'm in mole of CO2. All right, if I wanted to go farther so I could whittle down to just atoms, what would I be going to next? I can't go straight to atoms because that's just a single element, right? What's this thing called again? That's a molecule. So give me from moles to molecules. So where do I write that?
You write a mole on the bottom.
So 1 mole of CO2 contains lots and lots and lots, 6.022 times 10 to the 23rd, molecules of CO2. So I've whittled down from a liter, I've gotten to just a mole of things. My mole of things I'm now calling molecules. Now whittle down from 1 molecule of CO2, which looks like what?
The C in the middle.
C in the middle?
2 ligands of oxygen.
2 ligands of oxygen. You guys had this one? Or no, you get carbon disulfide on your request. Okay? So that's, you can see the 1 molecule, how many atoms of oxygen are in it? 2. Now, do I always have to draw these? Can't you look at the formula? It does really help connect what we're learning, but can't you look right here? Dioxide, 2 oxygens, right? 2 atoms of oxygen, but it's helpful so that you know what a molecule is and what an atom is, how they look different. So I'm going to put 2 atoms of oxygen are present in 1 molecule of CO2. And that's what I just drew over there. We counted them out first so we could see the relationship, the ratio. Whew, okay, that was a 3-stepper. Calculate. Anybody? Should it be a big number or a small number? Should be like a humongous number, right? 10 to the 23rd is on top over here. Anybody else? 1.34 times 10 to the 25th atoms of oxygen. And then sig figs, I'd round to 1.3 times 10 to the 25th. Whew. All right, so basically, guys, we applied 3 new relationships. 1 mole is related to how many particles? 6.022 times 10 to the 23rd. 1 mole is related to what kind of mass? Molar mass. Is there a specific number for that? No, you got to reference it in your table. 1 mole is related to what volume? 22.4 liters at 0 degrees Celsius, 273 Kelvin, 1 atmosphere. Those are our 3 molar relationships. We will use them extensively. Okay, so let me tell you what homework is before you leave me. Do you see where we just did the class examples? I'll do number 6 for you later. I want you guys to do 1 through 8 for me tonight. It says student practice. You guys see those? That is homework. 8 questions. Do the same exact process. Question, given, step, step, step. I need to see effort. So if I see no effort, I can't really help you out. Yes. 1.3. I just didn't kind of write it out. I think we leave in like 30 seconds. So go ahead and check out the children. I'll upload this video for you later. Yeah. I do on PS9. Yes. I'm sorry. It was on my warm up, but I skipped 2 slides ahead. PS9 in the box. I'll pass them back to you tomorrow. Is that okay? Yeah. So problem set 9 in the box, guys. Thank you.